Hello, you're listening to the Science of Everything podcast, episode 90, Climate Systems. And I'm your host, James Fodor. So in this episode, we've got a lot to get through. I'm going to be talking about the various effects on the Earth's climates, largely from atmospheric and also oceanic circulations of air and water, and how essentially the uneven distribution of solar insolation over the Earth's surface gives rise to the patterns of climactic differences that are found, obviously, across different parts of the Earth's surface. So in particular, things that we'll look at include geographic effects and seasonal effects on temperature around the world. Talk about air pressure and wind. We'll look at the coriolis effect of the Earth's rotation on the motion of air and water over the Earth's surface as they move around. We'll look at the main driving forces behind atmospheric circulation. We'll talk about circulation cells and also both high and low atmospheric circulation. And we'll talk about ocean currents and the role they have to play in determining Earth's climate. So that might sound like quite a lot, and indeed this will be a full episode. The unifying theme of this episode, as I've said, is climate systems. Although we won't explicitly be talking about, say, climate classification or climate change, I'm going to be discussing the key principles that determine essentially why climate is the way it is on different parts of the world. Obviously, at a high level of abstraction, there are many details that we won't go into, but at the end of the day, hopefully you'll have a much better understanding of, why some parts of the world are desert and some parts are tropical rainforest and so forth. And ultimately, it all comes down to redistributions of energy brought about by uneven heating of the Earth's surface. And we'll see that theme coming up again and again. So the recommended pre-listing for this episode are episodes 87, Geography of Planet Earth, and 88, Cartography and Earth's Seasons. Episode 89 on the atmosphere wouldn't hurt either. So as you can see here, we're building on a theme about trying to understand the processes that determine Earth's climate and weather conditions. So those previous episodes will help you out, especially the one on Geography of Planet Earth, where I talk about the different types of vegetation and weather patterns that prevail in different regions around the Earth. In that episode, I promised to talk about some of the reasons that these distributions of climate were the way they were. And this is the episode where I'm going to be making good on that promise and actually discussing some of the mechanisms behind that. So with that preamble, let's make a start and launch into the subject by talking about geographical effects on temperature over the world. So there are a wide range of factors that determine essentially the average temperature in a given place on Earth over the course of the year. Obviously, we know it depends on the season, but here we're focusing on geographical effects. So the first is latitude. So remember, latitude is effectively a measure of your distance away from the equator or how far away you are from the poles, sort of equivalent way of thinking about it. Solar insolation is greatest at the subsolar point. The subsolar point is effectively the point on the Earth's surface that is directly below the sun, or that you can draw a direct line from there to the center of the sun. That the subsolar point, or the line around the world that represents the series of subsolar points as the Earth rotates, is the region on the Earth's surface that receives maximal solar insolation from the sun. If the Earth had no axial tilt, the subsolar point would be exactly on the equator. But because of axial tilt, and also because of the rotation of the Earth about the sun every year, the subsolar point moves around the equator between the tropics of Capricorn and Cancer, moving back and forth between those 2 points across the equator from year to year. So, but more or less, you can think about the subsolar point as being close to the equator, as usually it's not too far away from the equator. So if solar insolation is greatest around the equator, then obviously, or at least on the first analysis, temperatures are going to be greatest around that area because that's where we're receiving the most heat. And on a sort of a first order of analysis, this is what we see. The equator is certainly much hotter than the poles, and indeed areas around the equator are tropical regions, in part because they receive so much energy from the sun. It heats those regions up and they tend to stay warmer more than other parts of the planet. So that's a big factor, as we discussed in the episode about cartography and Earth's seasons, the axial tilt and how that changes over the course of the year, and that leads to varying amounts of sunlight per unit area on different parts of the world, that is a huge driver of temperature difference, and in particular why temperature varies with latitude, with, as a general rule, cooler temperatures observed at higher latitudes. Another effect on temperature is that of altitude. Now, in the troposphere, which remember is the lowest level of the atmosphere, temperature decreases with altitude due to decreasing air density and also reduced ability to absorb heat because of that reduced density. So the higher in altitude you are, in general, the cooler it's going to be because there's less atmosphere there to retain that heat. Cloud cover also has an important effect on temperature because clouds reflect sunlight. Clouds are mostly white or whitish at least. That's showing you they reflect light, and when clouds cover an area, a significant portion of the sunlight that's impinging on that area is reflected back into space, and so you actually have a lower absorption of energy, thereby leading to lower temperatures over that area. Another important factor in determining temperature differences around the world is the phenomenon of sea breezes, also called onshore breezes, and the related effect of continentality. So these are all ultimately due to the fact that water has a higher heat capacity than land. And the heat capacity refers to the amount of energy that has to be absorbed or released in order to change the temperature by a certain amount. And as I think I talked about in a previous episode, I'm not sure exactly which one, water has a very high heat capacity, meaning that it requires lots of energy to increase the temperature of a given amount of water, much more than that of land. So this means that for a given amount of incoming solar radiation, the land will heat up more than the nearby sea. And conversely, for a given amount of time releasing radiation, say overnight when there's no solar radiation, the land will cool off more than the water will. So this means that water tends to moderate temperature changes over land. I explain this as being a result of the highest heat capacity of water, but it's also due to some other effects, such as the fact that water is it's a liquid, right? So it can transfer heat away from the region that's being heated up, say the surface of the ocean, via convection, cells of flowing fluid that transports heat away from the hot to colder areas, whereas obviously that's not possible over land. You can still have convection in the atmosphere, but the land itself obviously can't move around like that, whereas in the ocean you can. So that's another means by which the water is able to soak up more energy than the land is without equivalent increases in temperature. There's also the fact that water evaporates, and that uses up some amount of energy, whereas obviously land doesn't evaporate. So once again, there's another mechanism by which the sea heats up less for a given energy input, or cools down less for an equivalent energy output compared to the land. So this results in sea breezes, which I just mentioned previously. Essentially, when air gets warmer, as the air over the land does relative to the sea, because of the lower specific heat capacity of Earth relative to water that I just talked about, in convection and those other effects. That means the air over land also heats up relative to the air over the ocean. And when that happens, air expands. Hot air is, other things being equal, less dense than cool air. Effectively, that's because the molecules in the air are moving around faster when the temperature increases. And that leads to sort of an outward pressure force that causes them to become a bit less dense. And that reduction in the pressure over the land, which is at the higher temperature, leads to wind flowing. Wind is just the movement of air as a result of differences in air pressure that in turn usually result from differences in temperature. The air pressure differences that give rise to winds are generally not especially large. You're looking at differences of maybe a few percent, but that's enough to generate quite large forces and move substantial amounts of energy. So as the air over land heats up, it expands, becomes less dense. That leads to a pressure difference where the air over the sea, which is more dense, is going to be pushed towards and expand out, filling up the space of the less dense air over the land. This generates a sea breeze. The air is moving from over the sea over to the land, hence a sea breeze. And this is the pattern in the daytime when the land heats up more than the ocean. It reverses at nighttime when the land cools down faster than the ocean and the sea breeze reverses direction. So the effect of this sea breeze is effectively to moderate temperature changes in coastal areas. And it happens in a daily cycle, as I talked about in terms of sea breezes, but it also occurs on a larger scale seasonally. And this is the effect of continentality that I mentioned. So you can see maps, and I'll post one of these up on the Facebook so you can have a look. These maps show the difference in temperature annually in given regions of the world. So an annual temperature range, generally like maximum and minimum values from, say, the local summer to local winter temperatures. And of course, there's always a range because even areas around the equator have some hotter seasons and some cooler seasons, but around the equator it's very small. It's like a few degrees is the temperature difference between summer versus winter, because tropical regions have fairly constant amounts of solar insolation across the year, whereas the higher latitude is, the more variation there is between summer and winter. So generally higher latitudes have a greater annual range. But the effect we're interested in here is that of continentality, and that is, if you look at these graphs, you'll see that for the most part, inland areas, so regions in the center of continents, have much higher temperature ranges compared to regions at the edges of continents or around coastal areas. This is most evident in the inland regions of northern Canada and also eastern Siberia, where the temperature range from summer to winter is greater than 40, even over 50 degrees. Now that's compared to regions of, mainland, coastal, or at least relatively near the coast in, say, East Asia, Europe, or the Americas, where these temperature ranges are more on the order of 10 to 20 degrees. Obviously, there's variability there, but the point is that in inner regions of continents a long way from the ocean, there is a much greater range of annual temperature differences. And the reason for this is because the inland continental areas experience this effect that I mentioned, continentality. They don't have the moderating effect of the oceans to warm them up in winter and cool them down in summer. Effectively, the ocean serves as a big heat sink and heat source. It stores up heat when in summer times or during the day, on other periods when there's relative abundance of energy. So it stores up that energy and then releases that in cooler periods. It's thought that this is also relevant to global warming, because as the Earth warms up, a lot of that energy is going into the oceans, and there are concerns that there may be limits to the amount of energy that the ocean is able to absorb in this way, and that this might lead to sort of threshold effects where the warming of the atmosphere may accelerate or may increase in unpredictable ways because of the interactive effects of the amount of energy that's being absorbed by the ocean. Another manifestation of continentality effects is if you look at these temperature graphs, annual temperature graphs, with the months plotted on the horizontal axis and temperature on the vertical axis. And again, I'll put one of these up. Generally, coastal cities or regions, but they're often done for cities, have much flatter peaks. In fact, if you look at tropical regions, so areas quite close to the equator, they'll essentially be a flat line. And what that means is the temperature is basically the same all year. Now, for cities in the northern hemisphere away from the equator, what you would expect is to see higher temperatures around summer, so June, July, August, and lower temperatures in winter, December, January, February. The way these graphs are plotted, with January on the left and December on the right, you expect to see a peak in the middle. Obviously, in the southern hemisphere, you see a trough in the middle because winters and summer is reversed. So that's the case for all cities that are away from the equator. But because of the effect of continentality, cities that are much further inland tend to be much more sharply peaked, meaning that in summer they get hotter than an equivalent place, an equivalent latitude city near the coast, and during winter they get a lot colder. So you're much greater temperature extremes. And one example that I'm looking at here is Dallas versus San Diego. San Diego being on the coast and Dallas quite a ways inland, but at almost the same latitude. And Dallas has a much greater temperature range from what I'm looking at here, something on the order of about 20 degrees or maybe 25 degrees compared to San Diego, which is only about 10-ish degrees. This graph is not very precise. But the point there is that this great difference is largely due to the effect of continentality, the moderating effect of temperature extremes of the, in this case, Pacific Ocean compared to Dallas, which is a much further away from the coastline. Okay, so I've talked about geographic effects on temperature and also seasonal effects on temperature. Now let's talk a little bit more about wind and work our way towards the Coriolis effect. So wind is the horizontal movement of air across Earth's surface caused by density differences in between locations. Obviously, air moves from areas of high pressure to areas of low pressure. As I said, these pressure differences often aren't that large, maybe on the order of a few percent, although in extreme cases like hurricanes, they can be larger. Pressure is often measured in millimeters of mercury, which is just a sort of a conventional way of measuring it effectively. Effectively, the idea is that the height of mercury in some standardized barometer tells you how much the atmosphere in that particular location is pressing on the mercury, and therefore what height it's going up to. So the higher number means a higher pressure because the atmosphere is pushing more intensely on the mercury and causing it to move higher up the barometer measurement. Movements of air are caused by pressure differences, and these pressure differences in turn are usually caused by differences in temperature, so heating differences. As I mentioned before, on the Earth's surface, hot areas generally correspond to low pressure because as the air heats up, it becomes less dense, and therefore you have relatively low pressure. Colder regions have relatively high density and therefore relatively higher pressure. Winds redistribute energy away from high density regions to low density regions. Winds are named by the direction from which they blow, so the direction they are coming from. So easterly winds blow from the east, westerlies blow from the west. That's very important to keep in mind as to that it's always from which they blow, not the direction they're blowing into. The basic purpose or function of wind on the Earth's surface is to redistribute energy from the equator to the poles, because as I mentioned before, the equator and regions around that soak up on balance much more energy than the polar regions, and that energy will be balanced out, redistributed essentially according to the laws of thermodynamics from hot to cold regions, and that occurs partly through ocean currents, which we'll talk about in a moment, but also in large part through air currents and effectively wind. Wind is also responsible for the majority of waves on the ocean's surface and surface ocean currents. As we'll see later, deeper ocean currents are caused by different forces. We can also apply these concepts of differences in air pressure, wind, heating differences between land and ocean to understand the phenomenon of monsoons. So when I say the word monsoon, most people probably think of the rainy season, and that is how the word is often used. It means that, intense rains in a particular part of the year, but especially around the Indian subcontinent and Southeast Asia. However, monsoon in a sort of more geographic climactic context actually refers to the entire phenomenon, which includes both a rainy period and a dry period. So during spring and summer, the ocean, owing to the effects that I discussed previously, warms up more slowly than the land does. The land absorbs energy more rapidly and has a smaller heat capacity, so its temperature increases relative to the land. That increase in land temperature also heats up the air overlying the land, leading to warmer air and therefore a lower pressure. That warm air then expands and rises up, and as it rises higher into the atmosphere, gradually cools down. Now, at the same time, the air is being replenished, because it's moving up, it's got to be replenished from somewhere, otherwise you'll have a vacuum. The air is being replenished by a flow of air coming in from the ocean, which, remember, is cooler and therefore a relatively high pressure. So high pressure, cooler over the ocean, low pressure, warmer over the land. The high pressure water over the ocean then moves over the land as a result of that pressure gradient in the form of wind. That's effectively a large-scale sea breeze. But also because the air was over the water, it's absorbed some amount of moisture owing to evaporation. So that moist air moves over the land, then heats up as it moves over to the relatively hot land area. We now have moist, warm air, which, as I mentioned before, has lower density and so rises up. As that warm, moist air cools down as a result of moving higher into the atmosphere, remember temperatures decrease as you increase in altitude, the ability of that air to hold water decreases, because remember, the warm air has a greater ability to hold moisture than cool air. So as the parcels of air rise, they cool down. As they cool down, they lose ability to hold moisture, and therefore they lose that moisture in the form of rain. So that rain is ultimately moisture that's come from the ocean, being brought in by the pressure gradient of the high pressure over the ocean, the low pressure over the land, and then as the air moves upwards and cools down, it loses that moisture in the form of lots of rain. And then the cycle is completed as that air then moves at a high altitude back from the land over to the ocean to replenish the air that's been moving from the ocean to the land. So low altitude surface air moves from ocean to land, but at a higher altitude, it's the reverse. It moves from the land over to the ocean in this sort of cyclic manner. The moisture is lost as the air rises up and cools and loses its ability to hold moisture, and that occurs over the land, thereby resulting in lots of rains. This is what happens in the spring-summer period when the land heats up relatively more quickly than the water. In the winter period, it's the opposite. So exactly the opposite of what I just described effectively is what happens. Now it's the ocean that's warmer than the land because the land's been cooling down during the winter, but the ocean takes longer to cool down, so it stays warmer, it retains more of its summer heat, and now we have the breezes blowing out from the land to the sea, kind of like what happens at nighttime, sea breezes reverse. And now you've got the moist air rising, losing its ability to hold moisture, and then giving rise to rain. But instead of occurring over land, that now occurs over the sea because we've just sort of flipped that funnel of cyclic flow of air around. So now you have large rainfall over the ocean and much less rainfall over the land area. So that's the dry season during winter, corresponding to the wet season during summer, spring. So that's effectively the main phenomena underlying tropical monsoons. Now let's shift gears a bit and talk a bit about the Coriolis effect. Now, I have this vague feeling that I've talked about this before on the podcast, but I can't actually remember any particular episodes where I've discussed it. So if anyone does know when I've talked about this before, please let me know. But since I can't find it, I'll go over it again because I don't think I actually have. I just, for some reason, have the feeling that I've talked about it. The Coriolis effect is essential in understanding the patterns of air and water flow around, on a large scale, around the surfaces of the Earth and also in the atmosphere. The Coriolis effect is a result of the Earth's rotation about its axis. Because the Earth is rotating, everything that's attached to the Earth is dragged along with this rotation and travels as the surface of the Earth does. So that includes things like the continents, structures on land, and things like that. The ocean and the atmosphere are a bit different because they are fluids, and so they aren't rigid structures that follow through. They are generally brought along with the rotation of the Earth, but there's some residual resistance to that motion. I mean, if you imagine picking up a dish of water and then suddenly jerking it in one direction, or indeed a better example might be, imagine you were to spin around on the spot holding it in your hands out with your arms outstretched, the water will slosh over one side effectively, because you're accelerating the dish, but there's some lag time between when you exert the force on the dish and when the water actually feels that, owing to the fact that, well, a fluid flows and is not a rigid object like the dish is. Effectively, that's what's going on with the Coriolis effect, except it results from the rotation of the Earth about its axis and not, like picking up a dish and moving it. Basically, what's happening is the water and the atmosphere are being, to a small degree, left behind or lagging behind the rotation of the solid parts of the Earth. Now, the upshot of this, or the importance of it with respect to the motion of large masses of air or water, is that any such movements in the northern hemisphere will always be deflected to the right, unless they're right at the equator. The Coriolis effect doesn't exist if you're moving along the equator, but anywhere else, and it gets more intense as you move further away from the equator. But anywhere else, regardless of the direction you're traveling in, whether you're traveling to the pole, to the equator, or along one of the parallels, like along one line of latitude, the motion is deflected toward the right. So instead of being in a straight line, there's a sort of a bend to it. It curves towards the right. And in the southern hemisphere, it's the opposite. It curves toward the left. This is a result, as I said, of the rotation of the Earth. In fact, what's happening is not that there's a curving of the motion of let's say it's a parcel of air we're talking about. It's not actually that the air is curving. It's actually that the Earth is rotating underneath it. And so from the perspective of, if you would imagine drawing a map, it looks like the air is curving to the right. But in fact, it's actually the Earth that's rotating underneath it in the opposite direction. But it's often, because we're often interested in the frame of reference of the surface of the Earth, where obviously the rotation of the Earth is not visible on the surface of the Earth, because that's what we're interested in. From that frame of reference, it looks like the air or water is deflected to the right in the northern hemisphere and to the left in the southern hemisphere, but because of this rotational effect. Now, probably the most common understanding of the Coriolis effect is that it is responsible for the fact that water in a sink or a toilet rotates in one direction in the northern hemisphere and in the opposite direction in the southern hemisphere. Now, that is an urban myth. That's not true. The reason is not because the Coriolis effect isn't real, because it is. The Coriolis effect very much is real and has a large effect on large-scale masses of air and water in the different hemispheres. But the key there is large scale. It's like the force of gravity. It's only noticeable for relatively large systems. When you're talking about, say, individual molecules, the force of gravity is minuscule and you could ignore it. Likewise, when you're talking about the amount of water that's in a basin or a toilet or something like that, it's too small for the Coriolis effect to be noticeable. And instead, in those situations, the direction that the water spins in, if indeed it spins in any direction, it doesn't always, but the direction of spin will be determined by the exact shape of the bowl or basin, and also whatever initial small amount of angular momentum might have been accidentally imparted to the water. So they may have been unnoticeable at first, but as the total radius of the sphere or region of water shrank, because of conservation of angular momentum, as I've talked about in previous episodes, the rate of spin will increase to conserve angular momentum, and so it'll become more and more noticeable. So an initial small rotation that may not have been noticeable can become actually a very rapid rotation as the amount of water left in the basin is reduced. So that's another cause of whether it rotates left or right. But there's no systematic effect as a result of the Coriolis effect. It's just too small on those scales. But it is very important when we're talking about global masses of air, like continental scales. Then you absolutely have to consider the Coriolis effect. Now, it may be a bit counterintuitive that it operates in different directions in the northern versus southern hemisphere. I mean, how does the air, quote unquote, know which hemisphere it's in? Especially this is relevant when you're talking about hurricane systems or large masses of air. So particularly if we talk about cyclonic airflow relates to air that flows around a low pressure system. So a cyclone is an example of a low pressure air system. In a cyclonic flow, generally what you'll have is that the air sort of spirals inwards. There's a low pressure center in the middle, and so air is wanting to move to or tending to move towards that low pressure center, for obviously pushed in by the higher pressure from surrounding regions. But it doesn't just go straight inwards because because all of the airflows are deflected according to by the Coriolis effect, effectively by the rotation of the Earth. So it sort of spirals inwards. That there's a component of its motion that's brought about by the pressure gradient and a component to its motion brought about by the Coriolis force. And the combination of those is a spiraling pattern. This spiral always operates around a low pressure system. So in a cyclonic system, it always spirals counterclockwise in the northern hemisphere, but clockwise in the southern hemisphere. And it's obviously the reverse for high pressure systems. So how does the cyclone know, quote unquote, what hemisphere it's in order to behave differently? That's a bit counterintuitive. The best way I've come up with in thinking about this is that it's really a phenomenon is that the difference is really due to two factors. One is how we operationalize right and left, or clockwise, counterclockwise, which is essentially conventional. And the other thing is just because it's because of the way the Earth rotates. The Earth rotates from east to west, and that means that there is an asymmetry. If I am facing the equator in the southern hemisphere, that means that the rotation of the Earth is, obviously it's from east to west, but for me, in the southern hemisphere facing the equator, that corresponds to right to left. Now, if I'm standing in the northern hemisphere facing the equator, the rotation is still east to west, but for me, being in the northern hemisphere facing the equator, that is now left to right. So there's a difference here. Someone in the northern hemisphere facing the equator says that the sun rises on the left and sets on the right. But in the southern hemisphere, they'd say the opposite, even though they'd both agree that it rises in the east and sets in the west. The difference is just due to the fact of how we use left and right, and the fact of how the Earth equator works, and the fact that the equator bisects the Earth around its largest point and is perpendicular to the axis of rotation. So if you just sort of do the geometry of that, it has to work out that there's this difference in whether you're in the northern or the southern hemisphere. It's pretty much exactly the same thing when it comes to the Coriolis effect. It's just like what I said before, whether you're facing the equator in the northern hemisphere or the southern hemisphere affects whether you think the sun's moving from the left to right or right to left. It's basically the same thing with regards to flows of air, whether they're clockwise or counterclockwise. It's just because of the way the Earth rotates and the fact that the equator is perpendicular to the axis of rotation that we have this difference. So there's a lot more that could be said about the Coriolis effect, and to get the exact details of how and why it works where it does, you'd need to get quite mathematical, and so we're not going to go there. I'll just mention one other thing, that sometimes when you read about Coriolis effect, it explains it in terms of the different rates of rotation at different latitudes. So, the Earth is widest in terms of the circumference, is obviously greatest at the equator, and it decreases at higher latitudes. That's just how a sphere works. And so therefore, the rate at which a given point on the equator is moving as the Earth rotates is much higher compared to higher latitudes, obviously, because they don't have as far to go. The circles that they have to traverse in each rotation has a smaller circumference. So the idea is that the rate of rotation at the Earth's equator is greater than it is at higher latitudes, and therefore, if you move north and south, there'll be a deflection relative to, depending on whether you're moving away from the equator or towards the equator, because of that change in the effectively the Earth is sort of rotating under you at a greater or lesser speed than you are rotating, because you're moving to either higher if you go to close to the equator, or lower if you move away from the equator, rates of rotational speed, and that this is what gives rise to the deflection to the right or to the left, or east-west deflection. Now, this is true. This is a factor that contributes to the Coriolis effect, but it's not the entirety of the Coriolis effect. If you just looked at it from that perspective, it becomes hard to understand why you have deflection even when you don't travel north or south, even when you just travel east and west. But the Coriolis effect does operate in the east-west as well. But the exact magnitude is going to vary depending on all sorts of factors, including your latitude and other things as well. So to get the full picture, you really have to do a rigorous mathematical treatment as to exactly what direction the force is operating in. So those explanations in terms of different rotational velocities are true, but they're not complete. That's just one way of understanding why the Coriolis effect operates, but it's more complicated than that. Okay, so that's the Coriolis effect, and as we'll see, it's crucial to understand the Coriolis effect when it comes to talking about the driving forces of atmospheric circulation, which we'll move on to now. So, as I said before, the Earth's climate and weather is effectively a consequence of its illumination by the sun and the laws of thermodynamics. The laws of thermodynamics effectively stating that energy moves from regions of high temperature to regions of low temperature. So because there's unequal heating of the Earth's surface, more heating at the equator, less at the poles, the energy is going to flow on average from the equator to the poles. And that's what happens, and effectively it's what drives the large-scale circulation cells, which is the name for these large-scale circulations of air in the atmosphere, of which there are 3 in each hemisphere: the Hadley cell, the Ferrel cell, and the polar cell. And I'll talk about each of these in turn, but first I'll just give you a broad description of the structure of these cells so you can get a picture of what's happening. So imagine that we're looking at the Earth from side on, with the equator, so that's 0 degrees latitude on the left, and the North Pole, so we'll focus on the northern hemisphere, 90 degrees latitude on the far right. So along the x-axis, if you like, is latitude. And on the y-axis, we'll think of as altitude, so that's how far above the surface of the Earth we are. And the key marks along the x-axis, or along lines of latitude, are the equator at 0 degrees, 30 degrees, which are also called horse latitudes, and I'm not really sure why they're called that, but that's what they're called, and also 60 degrees of latitude. And finally, 90 degrees latitude on the far right. So we feel like we've divided it up into thirds, 0 to 30, 30 to 60, and 60 to 90. Now, each of these thirds has its own corresponding circulation cell. The Hadley cell from 0 to 30, the Ferrel cell from 30 to 60, and the polar cell from 60 to 90. And of course, there's an equivalent pattern in the southern hemisphere with just everything sort of flipped around. Now, each of these circulation cells represents, well, not exactly a circle, but a sort of a squashed circular pattern beginning on the bottom left. That is, if we're thinking of the Hadley cell, begins at the bottom left of our diagram that we're imagining here at 0 degrees latitude at a low altitude, and then moves up on the graph to still roughly around 0 degrees of latitude, but now at a high altitude, moves up to the top of the troposphere. Then it moves horizontally over the surface of the Earth, but now at a high altitude, so from roughly 0 to 30 degrees at 30 degrees latitude, it then moves down again. So from the top of the troposphere near to the surface of the Earth, and then it moves back southwards. So again, along parallel to the surface of the Earth, back to where it started from at around 0 degrees latitude and at a low elevation. So it goes up, across, down, and then back again. That's the Hadley cell. Of course, I've described it as a square and also talked about it as being a circle. That's obviously a strong idealization. It's not perfectly shaped like that, but that just gives you the general sense of where the flow is going. The polar cell is pretty much the same, except instead of at 0 to 30, it's up at 60 to 90 degrees. And the feral cell is similar, except it fits between the two cells, Hadley and polar, and it also goes in the opposite direction. So that is, the air starts at a low altitude at 30 degrees latitude, and instead of moving up, it moves northward, so it moves along our graph from left to right, from 30 degrees latitude up to 60 degrees latitude, and then it moves it moves upwards, so increasing in elevation, but staying roughly at a 6 degrees latitude, and then moves back southwards again, so from right to left on our graph, from 60 down to the 30 degrees latitude, and then downwards. So from the top of the troposphere down to near the surface of the Earth again at 30 degrees latitude. So that's just exactly the same as the Hadley cell, except shifted upwards and flipped in the opposite direction. And why it is different to the other two, we'll explain in a moment, but I'm just giving you the broad description of what the three main cells are and how they fit together. There's another element that I didn't mention, which is that all of these winds, because that's what wind is, large-scale motion of air over the atmosphere, is also affected by the Coriolis effect. So they don't literally move north and south, they're bent or curved towards the right in the northern hemisphere and towards the left in the southern hemisphere. In between the two Hadley cells, so the Hadley cell in the northern and in the southern hemisphere, there is a region that's called the intertropical convergence zone, and this is effectively where the two Hadley cells meet. And it's called the doldrums by sailors because often there aren't very strong winds in that region, because effectively this is where the two Hadley cells are meeting, and so there are winds within each Hadley cell, but sort of between them there's a relative lull. The exact location of the intertropical convergence zone varies according to the time of the year. So it lies around the equator, as you might expect, because the Hadley cells extend down to 0 degrees latitude at the equator, but it's not precise. It's affected by the location of the continents, and during the summer in the southern hemisphere, it sort of moves south, and then in the summer in the northern hemisphere, it moves to the north. So it sort of fluctuates around the equator. And the intertropical convergence zone is critical to understanding why these circulation cells exist as they do, especially the Hadley cells, which are sort of the main driving forces. So around the intertropical convergence zone, around the equator, the surface of the Earth is heated extensively, that is much more so than higher or lower latitudes, as a result of getting a larger quantity of solar insolation from the effects I've talked about before, because they're closer to the subsolar point. So around this region, around the equator, the surface of the Earth heats up more and has more heat being absorbed. That leads to, obviously, an increase in the temperature of the atmosphere overlying the land, and therefore a decrease in the density of that air, because warmer air has a lower density. So this results in these tropical low pressure zones. So the intertropical convergence zone around the equator corresponds to the equatorial low. And because it's a low pressure zone, you're going to have air moving into that zone, and that corresponds to the air that moves to the south in the Hadley cell along the surface of the Earth, coming back to the equator. And likewise in the southern hemisphere Hadley cell, you have air moving north that's moving into that tropical low pressure zone. What happens to the air that's actually at around the equator, around the intertropical convergence zone? Well, because of its low density, it tends to rise. And as it rises, it cools down. Remember that the troposphere has a temperature gradient that decreases with increasing altitude. So as this initially warm air becomes less dense, it rises. As it rises, it cools down. And as air cools down, as I mentioned before, its ability to hold moisture decreases. So what happens is that this excess moisture is released in the form of rain, essentially. And that's why there's a lot of rain around the equator, around the tropical regions, and also effectively why these regions are able to support tropical rainforests because they're warm, because they receive more solar insolation, but also they have a lot of rain because of these rising pockets of air. Begin with lots of moisture, but then lose that moisture as they rise up to higher altitudes and lose the ability to hold much moisture, and so release it in the form of rain. And this is also why around the equator you tend to have high amounts of cloud cover, because of all of this moisture that's being released by rising air. So this rising air that I've been talking about corresponds to the initial upward region of the graph. Remember the graph of latitude along the x-axis and altitude along the y-axis. The initial 0 degrees latitude region where the air moves upwards, staying around 0 degrees latitude but with now increasing altitude, that corresponds to this air that starts off warm, but then as it rises upwards, cools down and releases all that moisture in the form of rain. Once the air has risen and cooled down, it moves northward, again in the northern hemisphere, corresponding to the first horizontal component of the Hadley cell that I mentioned, up to around 30 degrees latitude, where it descends again. So the first northward part corresponds to the air moving high in the upper regions of the troposphere, but around 30 degrees latitude it descends again. Now, as it descends, it warms up again because the troposphere is warmer nearer to the Earth. Also, this air that's been moving, remember, has already depleted most of its moisture because of all that rain around the tropics that it released when it originally rose up. Now that it's coming back down again, it's warming up, but also it doesn't have much moisture left. It's already expended it. And so this incoming part of the cycle with warm, dry air leads to the existence of deserts around 30 degrees latitude, both in the northern and in the southern hemisphere. So this corresponds to the location of some of the deserts in around America and Mexico, also the Sahara Desert, and many of the other deserts in the world are sort of around this 30 degrees latitude region. Of course, there's variation with the location of continents and other things like that. But the reason for this is fundamentally because of the Hadley cells. That warm, dry air is coming down and creating what's called the subtropical high, which then leads to relatively low rainfall over these areas because there's just no moisture in that air that's coming down, or very little. The final portion of the Hadley cell that I need to describe is the closing of the circuit, the movement of the air from 30 degrees latitude across southwards, across the near the surface of the Earth, back to 0 degrees latitude to complete the cycle. Now, this air is traveling relatively close to the surface and so gives rise to surface winds. And the air, again, I'm talking about the northern hemisphere, is moving southwards, but is deflected towards the right because of the coriolis force. So these winds are effectively blowing from a northeasterly direction. They're typically called the trade winds, and these trade winds then bring us back to the equatorial low of the intertropical convergence zone and completing the Hadley cycle. So that's the basics of the Hadley cycle, which is sort of one of the key drivers because it's effectively transferring energy from the equator up to around 30 degrees latitude. The second major player in the circulation cells of the troposphere is the polar cell. The polar cell is more or less the same, except instead of being driven by a significant heat source around the equator, it's, or at least to a first order of analysis, again, good enough for our purposes, it is instead driven by the loss of heat from around the polar region, or in other words, the unusually cool region around the poles. The cold air around the poles, because they're not heated very much, is much denser than the warm, hot air around the equator. So you have high pressure areas around the pole. That leads to air moving away from the pole, that is southwards. So surface air moves southwards down away from the poles, away from the cold, high pressure air around the pole itself, until they reach around 60 degrees latitude as they connect up to the ferrule cell, where the air rises and increases in altitude and then ultimately flows back to the pole, completing the cycle. So it's effectively the Hadley cell, except instead of driven by the heat source at the equator, it's driven by the cold source, if you like, at the poles. The ferrule cell, unlike the Hadley and the polar cells, in which it's sort of sandwiched in between, is not driven strongly by any source of heat. In fact, it's not as well defined as the other two cells, but it links them together. It's sort of the cog that fits in between the Hadley and the polar cells, if you like, and is driven by them. So you have relatively warm air that starts around 30 degrees latitude at low altitude. So this is the warm air that corresponds to that over the desert regions around 30 degrees latitude that's come down, and it corresponds to the high pressure area around these areas. So this warm air moves northward until it gets to around 60 degrees latitude, where it rises again, and as it rises, it cools down, drops off its moisture as occurred around the tropical regions. So you tend to get a rain belt again around that 60 degrees latitude. That air then rises up, reaches near the top of the troposphere, and then travels south again, completing the feral cell. So these are the three main circulation cells that drive the global climate. Now, because of the pattern of these cells and the effect of the Coriolis effect, this gives rise to prevailing wind patterns in different regions of the Earth. So I mentioned that the fact that the two Hadley cells sort of combine or join at the equator, that means that there are relatively low surface winds around that area, the intertropical convergence zone, which is called the doldrums. So from there, moving out away from the equator, you have the trade winds, which exist around in the Hadley cell zone between the equatorial low region, where you've got that energy source at the equator, and the subtropical high. That's the 30-degree high pressure zone from the air coming down. In the feral cell, so on the other side of the subtropical high, we have westerly winds, which come from the west and the southwest, really. And so the south to north component of the winds is, again, due to the completion of the feral cell, whereas the west to east component is, again, due to the Coriolis effect, bending the air to the right. Again, this is in the northern hemisphere. So these westerly winds are very useful for airplanes to take advantage of them, because they can potentially travel faster when they're traveling with the wind. There are also polar easterly winds, which operate at the near the polar regions, but they're not sort of as important for navigational purposes as this is the trade winds and the westerlies. So this pattern of pressure and prevailing winds is, as I mentioned, one of the main drivers behind why we have the climactic distribution that we do. Although you also have to consider the distribution of land masses around the world, because that makes a big difference as well. But here we're just considering, we're ignoring that. So as I mentioned, you have the tropical rainforests around the equator because of the equatorial low pressure there, which means that you have relatively hot air, which is expanding upwards, losing its moisture. You get lots of rain. Whereas at the horse latitudes, around 30 degrees, you have subtropical highs where the air is coming downwards from a high altitude. It's already lost its moisture and it's heating up as it moves downwards, so you have hot desert regions, which is relatively little precipitation. Further towards the pole again, you have another low, which is called the subpolar low. And this effectively is the result of air that is moving upwards and towards the polar high as a result of the high density, high pressure zone over the pole because of the cold temperatures there. So just to summarize that, you've got a equatorial low around 0 degrees latitude, you've got a subtropical high around 30 degrees latitude, subpolar low around 60 degrees latitude, and a polar high 90 degrees latitude. So it goes low, high, low, high. So there's a regular pattern to it. This also explains why the polar regions are relatively dry. Remember, polar regions are generally desert or near desert regions, although we don't think of them as such, but they don't get a lot of precipitation. That's largely because the air is coming down from a high altitude, meaning that it doesn't have much moisture. It's already lost its moisture. That also occurs around the 30 degree latitude. Again, the air is coming down. Those are both high pressure regions where the air comes down. It does not have much moisture, and therefore you don't get much rain there. When air moves upwards, it cools, loses its moisture, and you get rain in those regions. That happens around the equator, and it also happens to a somewhat lesser extent around the low pressure regions at 60 degrees latitude, the subpolar low. So you tend to get more rain in those areas than in between, and that's why you get deserts both at the poles and also in between the 60 degrees latitude and the equator, around the 30 degrees latitude, where you have those high pressure regions. So that gives you an overall broad brush stroke picture of the atmospheric circulations and how they're driven by the Coriolis effect and differential heating of the Earth's surface. I now want to talk a little bit about high atmospheric circulation. Most of what I've been talking about up to this point is, well, the cells involve both the high atmosphere and low atmosphere, but mostly the focus is on relatively low altitudes, especially because that's what drives the main heat differences, because most of the energy is absorbed near the Earth's surface and then heats up the atmosphere just above that region. So you may have heard of the jet stream. there's actually more than one jet stream, but the main one that people talk about occurs around the polar front. So that's at the 60-degree latitude low pressure region. Of course, it actually varies quite a lot. It sort of wiggles up and down the latitudes, but you can think of it as being roughly located around this region. They occur around the tropopause. That's near the top of the troposphere, and generally westerly winds, so flowing west to east. And as I mentioned, their parts have a meandering shape over the latitudes, so they'll sort of point. There'll be a projection down a bunch of degrees of latitude, and then back up again. So that they don't just flow simply east to west, but they meander around. The strongest jet streams, as I mentioned, are the polar jets, which have wind speeds of up to a few hundred kilometers an hour, so quite fast. But again, these are at high altitudes, so around 10 kilometers, not at sea level. And jet aircraft sometimes take advantage of these for travel because they can substantially reduce fuel usage and journey time if they can take advantage of traveling in these jet streams. The cause of the jet streams, very simply, and ignoring the various subtleties, is effectively the convergence of westerly winds, which, remember, flow around the 30 to 60 degrees latitude, with polar easterlies, which again flow roughly from the 90 to 60 degrees latitudes. These are flowing in opposite directions, and so when they sort of converge, you get this very strong wind flowing from west to east, which occurs roughly at 60 degrees latitude, so at that convergence zone. Although, as I said, it meanders quite a bit. And those meanderings, that is the either southward or northward sort of pinching off of the jet stream, is called Rossby waves. And these are quite large, so, like continental size or a bit smaller than that. And they are one of the main drivers of day-to-day weather patterns at mid-latitudes. So these low-pressure regions, which sort of pinch off from the region of the polar front, or around the 60-degree latitudes, and can move into lower latitudes, bringing storms or cold spells. Obviously, there's a lot more to weather patterns in mid-latitudes than just that, but these Rossby waves are one aspect of that phenomenon, whereby meanderings of the jet stream can give rise to these low-pressure cells further south than you would normally see them. So that's mostly what I had to say about air currents. I also wanted to say a little bit about ocean currents before finishing out this episode. So an ocean current is a continuous directed movement of seawater caused by forces acting upon mean flow, particularly the Coriolis effect and wind and temperature and salinity differences. They're the main forces that operate on ocean currents. There's also some effects of tidal forces caused by the moon and also the sun, but I won't talk about those here. The shape of the continents can also affect these things as well, but again, I'm going to ignore that for the moment. So surface currents are found, unsurprisingly, on the surface of the ocean, and they're driven by large-scale wind currents, particularly those circulations that we talked about, the Hadley cell, the Ferrel cell, and the polar cells. So those directions that those winds are blowing in correspond in a fairly regular way to the direction of the surface currents in particular regions of the ocean. Of course, that's also going to be shaped by the distribution of the continents. Now, this gives rise to what are called gyres. So these are large systems of circulating ocean currents that are caused by large-scale wind movements. And effectively, there's a gyre that corresponds to each of the main oceans. So there's one in the North Pacific and one in the South Pacific, one in the North Atlantic, one in the South Atlantic, and one in the Indian Ocean, big gyres. The flow, as you would expect, is clockwise in the Northern Hemisphere and counterclockwise in the Southern Hemisphere. Again, that's due to the Coriolis effect. So these surface currents are mostly flows of the surface water, relatively low depths. But there are also much deeper currents, which are mostly caused by different forces. These are called thermohaline circulations, and these are large-scale ocean movements that includes deep currents. And unlike the surface currents, which is mostly, flows around the surface of the water, thermohaline circulations include vertical flows of water, so that is from high depth to low depth or vice versa. Now, these flows are called thermohaline because they're driven by two main factors: differences in temperature and differences in salinity. Thermo referring to heat and haline to salt. So warm seawater expands. It doesn't expand as much as warm air does, but it does take up somewhat more volume. And so it's less dense than cooler seawater. So warm seawater tends to sit above cooler seawater. So that's obviously going to lead to currents flowing when there's differential heating in some areas of the ocean to another. Also, saltier water is denser than fresh water because the salts sit in the spaces between water molecules, so there's more mass there per unit volume. So again, saltier water tends to want to sit below fresher water. So one simple way of thinking about what happens is that in particular regions of the world, especially around the sort of equatorial region, say of the Atlantic Ocean and also the Pacific Ocean, the surface water heats up because of the energy that it's absorbing from the sun. It then travels either to the north or to the south. In the Atlantic Ocean, say, we'll take that example, the water tends to travel sort of along the coast of the Americas and over to Western Europe. This is actually called the Gulf Stream and its extension into the Atlantic, the North Atlantic Drift, and effectively is a current of relatively hot water, which brings with it relatively warmer temperatures and is thought to contribute to the relatively warmer climate of northwestern Europe compared to, say, comparable latitudes in Canada or elsewhere in the world. But anyway, this is just one example of a current of relatively warm air which moves from the equatorial regions up to more northerly regions around Iceland, Greenland, and up in the Arctic Ocean. Now, when it gets there, first of all, it's as it travels there, it's gradually evaporating, so it's becoming more saline. That increases its density, but also, particularly when it gets to colder regions, it cools down. It releases heat to the air around the Arctic Ocean, Greenland, and so on, where it's much colder. And because of these two factors, becoming more saline and cooling down, it becomes more dense and therefore sinks to the bottom of the ocean. Obviously, this takes place over hundreds of kilometers, but it gradually sinks. And then as it does so, it travels southwards down across the bottom of the Atlantic Ocean, down south right to the Southern Ocean near Antarctica, where it then travels in an easterly direction. Then it goes up into the Pacific Ocean again, where it eventually upwells, that is, comes up near the surface and then heats up again around the equatorial regions and then flows back down across the Pacific Ocean, meeting up in the Atlantic Ocean again. So there's these big complicated circulations. I won't try and describe them in detail because they're too complicated to describe without a map. But you get the basic picture that in certain regions of the world, you have, particularly around the equatorial regions and Pacific, Indian, and Atlantic Oceans, you have warm surface air which then moves north or south, cools down, sinks, and then moves then to another location on the Earth where it sort of links up and repeats the cycle again. So these currents can result in the transfer of a lot of heat and are very important in mediating global climates and relating to climate change, as I alluded to before. They are also important in that they transfer a larger volume of water. As you might expect, you're talking about the volumes of entire oceans effectively moving about. They are much slower though than surface currents. So we're not talking days or weeks. We're talking hundreds, even thousands of years for some of the bottom level water to complete these cycles that I mentioned. So it's quite a slow movement, but nevertheless still very important. So that's all I wanted to get through in this episode. Hopefully it made sense. I know there were quite a few concepts in there, but the main things to bear in mind is that what we talked about in this episode were flows of energy brought about by differential heating in the Earth's surface, particularly more heating around the equatorial regions compared to the polar regions. This gives rise to geographic differences in temperature and also the effect of continentality, whereby the range of temperatures in continental regions is much higher than in coastal regions because of the moderating effect of water. I talked about monsoons as effectively a large-scale version of sea breezes, the continentality effect again. And then we looked at atmospheric circulation. I talked about the Hadley, the Ferrel, and the polar circulation cells, as they're affected both by transfers of heat from ultimately from the equator to the poles, and also the deflection of air towards the right in the northern hemisphere and the left in the southern hemisphere as a result of the coriolis effect. One thing I wanted to note is that the fact that there are 3 of these circulation cells on Earth, the Hadley, the Ferrel, and the polar cell, as opposed to 5 or 10 or 20 or however many, depends on a number of factors, including the rate of rotation of the Earth, the size of the Earth, and also the amount of energy that it receives from the sun. If you look at Saturn and Jupiter, planets, the gas giant planets, you'll notice that they have bands of clouds as well. And effectively, these are not exactly the same, obviously, but a similar sort of phenomenon, differential heating of the planet's surface and therefore flows, circulation cells of gases in their atmosphere. But they have more than 3. They have more bands than the Earth does. But it's a similar phenomenon, and those planets rotate at different speeds and they have different amount of heating from the sun. So those factors will change the number of circulation cells. But on Earth, it's basically 3. We also talked about the jet stream and the ocean currents and the distinction between surface currents and the thermohaline circulation of the deep ocean currents. So if you enjoyed this episode, please give the podcast a favorable review on the aggregator site of your choice. You can also support the podcast by going to Facebook and typing in the Science of Everything podcast and finding our page where you can like the show to show your support and also get updates about new episodes and some visual content that I post there sometimes as well. You can send me an email. My address is fods12@gmail.com, fods12@gmail.com, to give suggestions about future topics or feedback, questions, suggestions, or just to say hi. I always like to hear from listeners. So thanks for listening, and I'll talk to you next time.